Okay, guys, so now that we have an understanding, or hopefully have a good understanding of work from our unit on work, we can put that concept to use thinking about what we're going to call simple machines. Simple machines. And simple machines, we're going to talk about three examples of simple machines, three types of simple machines that are designed to make work easier. To make work easier. Now, some of you may be getting amped up thinking, well, machines sound like sort of a fun, exotic thing to discuss. I hope you won't be disappointed. These simple machines are really pretty simple. The three that we're going to discuss are the ramp, which is sometimes called you'll hear me call it an inclined plane. It's a plane or a flat surface. It's inclined. So a ramp, we'll talk about pulleys, so the pulley, and then we'll talk about the lever. Those are the three that we'll discuss. So these are not maybe the most exotic examples of machines, but these are the three we'll discuss. And actually, in this video, really, it's just the ramp. The ramp is the one that we're going to focus on in this video, the ramp or the inclined plane. All three of these, under certain circumstances, can make work, and by work, we're thinking about the physics definition of work. They make work easier. What they don't do, and this is going to be a key concept here, is that these simple machines, they may make work easier, but they do not do work for you. Okay, so they may make the work easier, but they do not do the work for you. And so the central principle here that we're going to work off of is that the work you put into the machine, so work in, is equal to the work you get out of the machine, work out. So this is going to be our principal guiding equation right here. The work in equals work out. And so this is a really important idea here. By work in, what I mean when I say work in, this is the work you do. So the work you do. And the work out, this is the work the machine does. And one way to think about the work out, this would be the work you would have to do if you didn't have the machine. So work without the machine if you didn't have the machine. So work without the machine. And that might sound a little bit abstract, but I think if we look at an example, maybe we can make some sense of this. So, and we'll uncover exactly how a machine such as an inclined plane or a ramp could make work easier. So, without further ado, let's do that. So, let's imagine I'm moving and I get a moving truck. So here's my moving truck. Here it is. And here's my moving truck, and here's the ground. And I have to take this really heavy appliance, maybe it's like a refrigerator, and I've got to get this refrigerator, here's the refrigerator, onto the moving truck. So here's the refrigerator, and maybe this thing's really heavy. It has a mass, let's say, of 100 kilograms. So it's very heavy, and I have to get it onto the truck, and let's say that the truck, so let's say refrigerator, put it over here, the mass equals 100 kilograms, and the height of the truck, this height right here, height is, let's say it's 1.2 meters high. And maybe I'm not strong enough. I can't lift this refrigerator on my own. I can't lift it up 1.2 meters to put it on the truck. I'm not strong enough to do that. But I somehow have to get this refrigerator onto the truck. And so what do? We use a ramp. So I might take a ramp here that goes up to the back of the truck. And by using this ramp, maybe now I can exert enough force. If I were, for instance, put this, maybe I go ahead and I put the refrigerator, I put it on a little dolly so that it has wheels right here. And now I can successfully wheel it up the ramp. And this is what I mean when I say it makes the work easier. In theory, you could just lift the refrigerator straight up and put it on the truck, but using the ramp, it's a little bit easier. Now, let's revisit this idea that the work you put in equals the work you get out. In other words, it's the same amount of work regardless of whether or not I have the ramp. If I were to lift this thing straight up, it would be exactly the same amount of work. So let's see what I mean by that. So what I'm going to say is, again, work in equals work out. So I'm going to say force times distance FD with the ramp is equal to FD without ramp. So FD no ramp. If this is true, let's go ahead and calculate both sides of this. Well, it's easy to figure out the right-hand side. What would be the force times distance without the ramp? Well, the force would be the weight of this thing. So that's 100 times 9.8. So 100 times 9.8 is F. So 100 times 9.8, that's 980 newtons. So that's my force. That's F, mg. Right? And the distance, well, how high do I lift it without the ramp? I have to lift it up 1.2 meters. So the right-hand side, go ahead and calculate that, 980 times 1.2, and I get 1,176 joules of work. So if I use the ramp, I've got to do that exact same amount of work. I'm going to, no matter what, the ramp's not going to do work for me. I have to do this much work. But let's maybe see that this ramp, let's say that from here to here, this distance, right? This is my distance with the ramp. Maybe this distance, the length of the ramp, maybe it's, I don't know, maybe it's 2.4 meters. Maybe it's 2.4 meters long. So if I go ahead and do FD with the ramp now, well, now my D here is 2.4. So you might ask yourself, okay, well, what force do I have to exert, right? I'm going to have to push this thing up the ramp with some force. So what is this F if the ramp is 2.4 meters long? Well, let's go ahead and calculate this. Now I can say if 2.4 times F has to equal 1,176, then I can see that the force I have to exert is going to be 1,176 divided by 2.4, which is going to be 490 newtons. So take a look. Without the ramp, this is the force I would have had to use, 980 newtons. That was too much force. I couldn't exert that force. But by using the ramp, I only have to exert 490 newtons, right? I've reduced the force. In fact, you might be able to see that this is exactly half the force. So I've been able to lift this heavy refrigerator by only exerting half of the force that I would have to without the ramp. So that's the benefit. Now the trade-off you can see, hopefully, is that even though I've only had to use half the force, I had to do twice as much distance, right? So this is my D. The distance was twice as much. So there's a trade-off here. I don't have to exert as much force, but I have to exert that force over a longer distance. That's the trade-off. And so the work without the ramp equals the work with the ramp. So there are certain times when using a ramp or an inclined plane helps you out. It gives you an advantage, okay? And what we call this advantage, we call it mechanical advantage. And this is an important concept. All of these simple machines, the pulley, the lever, the inclined plane, they all have the ability to provide what we call mechanical advantage, which I'll abbreviate MA. And basically the mechanical advantage, you can think about it as how much easier the machine makes the work. So how much easier the machine makes the work. So in our case up here, we saw that I was able to lift this heavy refrigerator by only exerting half the force that I'd have to without. In other words, in this case, the ramp doubled my input force. So we would say that this gives a mechanical advantage equals 2. The 2 meaning it doubles my input force. So I only put in 490 newtons, but I got 980 newtons out. So it doubled my input force. That's what mechanical advantage means. And to calculate the mechanical advantage, there's two ways. The first way is to take the ratio of the force you get out over the force you put in, and that's what we just did up here, right? I said mechanical advantage was 2 because I got 980 out and I only put 490 in, and this was equal to 2, right? That's where I got the 2 from. But there's another way we could have done it, which is to take a look at the lengths, right? I could have taken 2.4 and divided by 1.2. That would have given me 2. In other words, I could also say that this is the distance I put in divided by the distance I get out. Either of these equations can be used to calculate the mechanical advantage. And just to remember, when I say in, what do I mean? In is the what you put into the machine. In other words, this is the force or the distance with the machine. And out is what the force or distance if you didn't have the machine, so without machine. So without the machine, back here, to use this example again, without the machine, I would need a force of 980 newtons and a distance of 1.2. But with the machine, it's only 2.4. It's 2.4 meters and only 490 newtons. Hopefully that makes sense. And this is how we can go ahead and calculate the mechanical advantage. Frequently, it's easiest, if you're like looking at a ramp, it's easiest to use this expression right here, because you can measure the distances in and the distances out. This sometimes is harder to measure. I'm going to make a distinction right now that we'll investigate in class later. This expression, distance in, distance out, this is sometimes called the theoretical mechanical advantage. Theoretical. And the force in over, or force out over force in, this is what's sometimes called the actual mechanical advantage. So make note of that. We'll discuss that in class, what that means. Theoretical versus actual. To wrap this up, let's try another example. Let's say I have a ramp here, and here's a ramp. And let's imagine that this ramp is let's say it's 0.7 meters high. So this vertical distance is 0.7 meters, and do that again. So this distance right here, 0.7 meters, and the length of the ramp from here to here, this length from here to here, let's say is 2.4 meters. And we could say, what is the mechanical advantage? We could calculate what's the mechanical advantage. So what's the mechanical advantage of the ramp? That's what we'd like to know. And so based on this, if I go up to my equation for mechanical advantage, I don't know anything about the forces, right? I don't know anything about force out, force in. All I can measure here is the distances. So I'm going to take distance in over distance out. So distance in over distance out. And what's the distance in? What's the distance out? Well, again, in is what I have to do with the machine. That's the 2.4. Distance out is without the machine. In other words, if I had to lift it straight up, 0.7. And so here we can figure out what the mechanical advantage is. Go ahead, 2.4 divided by 0.7. And this is a mechanical advantage of, that ends up being about 3.4. No units on mechanical advantage. It doesn't take any units. So 3.4 is the mechanical advantage of this ramp. It's 3.4 times longer than it is high. Well, what that means is that if I had to lift something, so maybe I am going to push something up this ramp. I've got some sort of a crate here. And let's say the crate has a weight, or let's say it has a mass of 5 kilograms. And we might want to know, well, how much force would you need to use to lift the crate? So what force? What F to push crate up ramp? Right, like what force do you have to exert here? What F is necessary to go ahead and push that crate up the ramp? Well, now that we know the mechanical advantage, it's pretty straightforward. Because when we say that the mechanical advantage is 3.4, that means it's my input force, F, is going to be the weight of this divided by 3.4. In other words, a way to calculate this is to use this expression right here, force out over force in. I'm going to use that. I'm going to say force out over force in equals 3.4. So force out over force in equals 3.4. Okay, well, what's the force out? The force out is that's without the machine. In other words, it's the weight of this thing, mg. So mg 5 times 9.8 is 49 newtons. So 3.4 equals 49 over F. So if I solve for F, I get F equals 49 divided by 3.4, which is what I said at the beginning, right? The whole point of the mechanical advantage being 3.4, that means you only have to exert the weight divided by 3.4. So 49 divided by 3.4. This is about 14.4 newtons. 14.4 newtons. So I can lift this 49 Newton crate by only exerting 14.4 newtons of force. All right, that's all for now. Hope that makes sense. We'll practice it in class.